Our next presenter, AI ML Interface Engine Software for High Reliability Application on Space Qualifiable Hardware by Pablo Ghiglino.
Hello everyone. Yes, my name is Pablo Ghiglino. I pronounced it correctly. I'm here to present the work we have been doing at the software level for artificial intelligence execution on kind of deterministic and towards a space qualification execution of AI on board. I'm the founder of a company called Klepsydra. It's a small company based in Switzerland. We are 15 people, and most of our work we do is related to AI. It's quite a deep tech, so bear with me. Very C++, so also bear with me, and I'll show you how the thing works. So let's start showing you a little demo. We presented this last year in a conference in Nice, in France, called the EDHPC, organized by ESA. This is a LX2160 space processor, 16 cores. So we managed to run 3 different AI algorithms in 4 core each. We did 4 cores for other things. So we could do the very right coronal mass ejection detection using AI. There was a very interesting keynote to speak about this yesterday. In the middle, we do localization, geolocalization using AI. So we just by looking at the picture, we can see lat long. We can calculate lat long. And on the leftmost is cloud detection, so detecting of clouds on space. That is something we did together with the Barcelona Supercomputing Center. They're going to present something about this later today. And the tool we use to display the thing is the, most of you may know this is the OpenMCT. We just use it for visualization purposes. It's not that we use it for telemetry or anything else. But this is a little bit what we do. So it's running different type of algorithms. We don't necessarily build the algorithms. But what I'm going to present is the innovation we have been working on in order to execute this efficiently on edge. Oops, sorry. Okay. So going back to the base, I presented it last year, so I'm going to go quickly because most of you may have seen it already. So the core of our research is lock-free programming. So everything we do is related to lock-free programming. That means we use something called atomic operations. These atomic operations allows you to carry out race condition or avoid race condition without having to do any mutex in the system. So they're based on something called CAS, compare and swap, which is basically a type of instruction that tries to write something on a particular memory until it's left in a consistent state. So basically, when we're running AI on the edge on a multi-core processor with parallel threads, there is no a single mutex in the system. Everything is done without any mutexes running. And the base of this is what we call the develop. It is algorithm here. It's a lock-free ring buffer. It's inspired from techniques used in the financial trading. Believe it or not, financial trading has done a lot of work in order to squeeze performance of big servers to do as many transactions as possible against the stock exchanges. I was fortunate to work many years on this sector, so I learned some of these techniques and applied them to aerospace processors. So the loop is a lock-free algorithm that is like a parallelization framework. It's a multi-threading framework without being really any threads involved. In this case, the algorithm is able to absorb data coming from multiple sources in parallel at whatever speed, variable speeds as well, variable amount of data, absorb it all without any logs, like I said, and streamline it to be processed in one single thread. So this is how the thing works. So multiple threads coming in with data, streamline one thread to do the processing. Why is this so interesting? Because then the developers using this technology don't need to work worry about any multi-threading coding. No? We have another algorithm for multiplexing, but this is kind of out of the scope. But just for you to know, the loop is very efficient, very low power. So this is a demo we have done for another completely different sector, for self-driving cars, where we have the onboard computer receiving data from 15 different sensors, including multiple cameras, LiDARs, etc. And with this event loop, it's possible to keep processing the data throughout the execution, while if you use conventional blocking queues or any other techniques, the system will collapse. So this is the main benefit of the event loop, this capacity of being able to keep processing with low power and at the same time having a very high throughput of data. So how these concepts relate to artificial intelligence? No? This is the key thing. This is a key element I presented last year. Again, I will go more or less quickly. But there are two ways of parallelizing data processing for artificial intelligence on a multi-core processor. The traditional way is parallelization. You have to carry out the matrix multiplication of the convolutional layer. You split it into smaller bits, identical in size, parallelize this, and then come back with the results. No? This is what OpenMP and other Eigen and other tools can do for you. But there is another technique, which is the pipelining, which works a little bit more like an assembly line, where you split your algorithms, and each part of the algorithm is processed in a different thread. So this is the main concept of this pipelining. It has seen a resurgence in the academic world because of it has again similar features, low power and high throughput, as opposed to parallelization that has a very high power consumption. So what we have done is combine the two things in what we call, from the marketing perspective, the two-dimensional selling model. So when we try to sell the thing, we call it like this. But internally, it's basically that there are two types of threads. So when we talk about pipelining, as you can see in the leftmost image, we have our AI algorithm. I don't know how familiar are you with deep learning, but a deep learning algorithm looks like a number of operators to be executed in a interconnected, either sequentially or in a graph. So we say, okay, this portion of operators go to the first core, this other portion to the second core, etc. And in parallel, we also support the parallelization. No? So we also support both options. So you have a very heavy convolutional layer, which is the most traditional one, well-known operator in deep learning. You can split the convolutional layers as in parallelization as the classical approach tend to do. So empirically, we have been testing this, and we have realized one thing, which is that if we do a lot of pipelining, so splitting the algorithms in different cores, we get very low power consumption, so substantially lower than TensorFlow-Lite, for example, maybe 1/3 or 1/4 of the power consumption required, or CPU power required by the TensorFlow-Lite. However, the latency is not great. The latency will be bad. So if you need a real-time application, don't go for this. Don't do a lot of pipelining in your solution. On the other extreme, the rightmost diagram, if you do a lot of parallelization and little pipelining, then you get very low latency, but the power consumption grows a lot. So this is ideal for the case of real-time operations, no? Like planetary landing, in-orbit servicing, these kind of things. You don't care so much about power at the moment that you're doing your mission. What you care about is to be able to react in real time to whatever events are happening. While the other approach, the low power, is more like typical telecom scenario. So you have massive volumes of data coming, you need to do these FFTs on board, these fast Fourier transforms, and you want to reduce power consumption as much as possible. In those cases, you are more interested in the pipelining. And somewhere in the middle, there is an optimal solution where you can get the optimal throughput. I say somewhere in the middle because it's not clear exactly. We haven't found a formula for this. So empirically, we have found that certain combinations have a substantial increase in throughput. One thing we have seen here is related to Raspberry Pis. I will show you this in a minute. But in any case, in order to find this optimal solution, what we have developed a little tool called Klepsydra SDO, I always say the joke that the original name was Layer Streaming Distribution, LSD, but it will bring another type of clientele to the company. Anyway, the real name is SDO, and what it does is convex optimization. Basically, it's carry out a convex optimization of these different threading approaches, which layer goes to which core, which layer to parallelize, etc., and then it gives you the optimal solution. This is how the thing looks like. So we're using kind of pseudo AI to solve an AI problem here. Beyond that, one thing that we are working on at the moment, which is the next level in terms of optimization. So first, we started with we have worked in 3 layers of optimization. First is the event loop, which can carry out this processing very efficiently. Then we build this SDO tool, which is able to optimize the solution further based on how distributing the different elements. And we're working on at the moment is something related to the so-called network architectural search. Maybe some of you that are working with AI know about this, but the concept behind means you are trying to when you train your AI algorithm, you not only care about precision. Precision is of course the most important element in your fitness function in order to do the AI training. But you also care about performance. So you include your hardware in the loop, and every once in a while during your training cycles, you execute the model in the target computer, receive feedback, and see how is the performance. And you feed this into your fitness function in a weighted manner, no? And what we have seen, or what the literature is showing as well, is that with architectural search, by dropping the precision a little bit, something between 1% and 5%, you can get substantial performance increase, no, in the target computer, up to 50% reduction in latency and other things. So this is quite, and this is done. What I'm showing here is all standard. It's not our software. This is kind of a standard in the academic world. What we have here to do this is the so-called model generator. The model generator basically tests different, more or less random variations of your AI algorithm in order to find this optimal solution. So with this, basically, what this tool is doing is optimizing the network so it's run very efficiently in the target computer. So combining these 3 things, so the event loop, the SDO, and the Klepsydra in the loop, very complex models can be deployed to small computers like the Raspberry Pi. No? That's the key thing. So there are models that are extremely complex. I will show you in a minute. That can consume a lot of resources, and in principle, they're not made to fit into these small computers. But using this kind of optimization process, you can actually fit them there. So I will show you here a few examples of this. First. We have been running this in this good old set board. No? Everyone probably knows the set board. Is this Xilinx Sync 7020, I think it is. Has a very small FPGA, an ARM, 2 cores of ARM 32. And there we managed to run, again, a model also developed by the Barcelona Supercomputing Center, the so-called ship detection model. No? So you can see there are ships being more or less, I don't know if you see it, but they are highlighted in a blue rectangle. So this can run in the set board. So if you try this with TensorFlow Lite, it won't run. It will just crash. But here we managed to run. It runs one image every 5 seconds. It's not massive, but at least it's able to perform this task. And then we come to what I mentioned earlier about the Raspberry Pi. So on the Raspberry Pi, we have been running for a customer several different models related to lunar landing. We ran the first one we ran was for relative navigation, where we identify craters, and then with this you can more or less do like an optical flow, more or less, but AI-based. And this we ran in the Raspberry Pi 3B Plus with a latency of 12 seconds. One issue that I was going to mention with the Raspberry Pi is the pipelining can be only done in a limited manner. The reason is that we are still investigating, but there is something related to the FPU units. associated to each core that you cannot run some things in parallel in two of them. We're still trying to investigate this and talking to the Raspberry Pi fellas, because it's a very complex issue. It doesn't happen always, but in some instances, with certain specific type of convolutional layers, you cannot run them in parallel. So it's quite deep issue. Another model that we run is the so-called LunaNet. We also built this with another university, the Universidad Carlos III de Madrid. Again, we capture an image from the moon, and we can determine the lat and long based on information coming from previous missions. In this case, the Raspberry Pi was performing quite well. We managed to do it in 3 seconds. So this is quite a nice result. And then we come to one of the heaviest model we have ever run on the Raspberry Pi, which is hazardous terrain detection using AI. So this is a massive model. We need to do tiling, 100 tiles of this image, as you can see here. Each tile takes 1.5 seconds, which means that the total image takes 150 seconds approximately. In an FPGA, we have tried the same thing, and we can speed it up to 100 times at least. We have a version of our software running on the FPGA, but I will go back to that later. But this is one of the things. So this is the kind of thing we're doing. Now, even at this level, we didn't go to the Klepsydra in the loop. We only focus on the event loop and the SDO. And even then, we managed to run something at least. No, exactly. So it takes 150 seconds, 2.5 minutes to process the whole image. But again, if you try with any other tools, it will just crash. So at least it shows that it's possible to run some of these things that otherwise wouldn't be possible to run on these kind of devices. Okay, so moving on. I will back to FPGA, like I said earlier. Another project we're working as well in Europe with Aspire Global is to try a solution for accelerating GPUs. In this case, we are using the event loop to orchestrate how things are executed in the GPU and parallelize as much as possible using this concept of streaming that the GPU has. And we have managed to achieve a substantial performance increase. This year there will be an in-orbit demonstration with them. This is one of the highlight projects of the year. It's having quite complex, actually quite challenging, but we managed to get some performance increase here. This is well, it was mentioned yesterday. I think it's a Media Tegra. It's quite old, but still is used in some space missions in Europe. Another project we are working on is with a company called Ramon Space. Maybe some of you can hear of them. They have a strong presence here in the US, not so much in Europe yet. It's a hardware accelerator. In this case, what we're doing is accelerating as well, orchestrating, similar to the GPU, but via space wire. The space wire will be the main way to communicate between the CPU and this accelerator. This is one of the things we're working on at the moment. I'm just showing you a little bit of survey of what things can be done with this kind of lock-free concept, no? What things can be orchestrated. And what we have seen in all these cases is combining the execution with the orchestration of the event loop. Plus the SDO, you always get some kind of benefit in the performance of your hardware accelerator. Another probably the most important project we're doing this year is porting this technology to two things. First, to Artem's operating system, Artem 6, and also to port the software to the GR740. So these are the two main things that we're working on this year. We're also collaborating with Barcelona Supercomputing. So it's one of our partners on this. And we got some results already. So this has been quite a journey, but we're getting there. And one of the key things is we're going to use the multi-core features available on Artem 6. It's called Artem 6 SMP. And I was hoping to have the results for this week, but unfortunately they are not yet ready. But what we do have is results on a single core. And this is already quite interesting. We run it at the set board and compare with the results we did for a previous project on the set board. And we can see that already the performance is better when compared to Linux. So if we remove all the Linux FAS and other elements and we stick to the RTEMs, you will see already a substantial benefit in performance. We hope to see even better performance when we go to multi-core. So this, like I said, this is about to be ready. So we will publish this in our website when they are ready, possibly in the next couple of weeks. So, but the results are quite good already. It's quite promising. The main difference with respect to the traditional Linux parallelization is that here everything has to be using thread affinity. So when you parallelize with OpenMP or other tools, you usually don't care in which thread goes to which core, no? You can do it, but the main thing, you just let the system decide what is the most optimal solution. Here it's not possible anymore with RTEMs. In RTEMs, you need to really tell that things are going to this core or that core. This is quite an important feature, and this has implication in how to optimize with our SDO tool that now has to take into account this concept of the cores that we are using. Another project we're working on is FPGAs, especially with Xilinx. Similar concept. One portion of the AI model goes to the DPU. Whatever doesn't fit in the DPU because it's not compliance with Xilinx or any other reasons, doesn't fit, we put in the CPU. And then we coordinate the two things, again, using the SDO, event loops, Klepsydra in the loops, etc. So this is a big project we're doing as well at the moment. It has been running for a couple of years with a Swiss space entity that is quite well known at the moment, but I cannot mention the name. Exactly. So this is the concept of the FPGA connector. You have your network. You see which part of the network can actually be deployed to the FPGA because it's not always possible to deploy the whole thing. So this is how the thing started to come about. And the last thing we have been doing, or one of the most recent things we have been doing, is running our benchmarks on the PolarFire. The PolarFire RISC-V. The performance with respect to the Raspberry Pi is horrible. I have to tell you that. They are more or less equivalent, but because the RISC-V doesn't have a V extension, the PolarFire, the performance is really bad. I mean, it's like 5 times worse than the FPGA, which costs 1/10 the price of the PolarFire Icicle. However, if we compare to TensorFlow Lite, the performance of this concept that I mentioned, this pipeline is massive. We get substantially performance improvement running this approach. Soon to come, very, very soon to come, is the RISC-V of RTEMs as well. This benchmark run on Yocto Linux, but very, very soon we will also get the results in RTEMs. This is also being done as we speak. Similar to the mobile net. In this case, however, there was not many benefits in the CPU consumption, but massive benefits in terms of latency. So it depends on the network. This is quite an interesting thing. Depending on the network, there are many things that are variable and not necessarily within the control of the software libraries. Another thing we're doing also with Leonidas, Barcelona Supercomputing, is this deployment to the OPSAT. It's an experimental satellite of ESA, but I won't speak much there because we have a video live in the Flight Software Workshop that you can see and understand what we're doing exactly there. And then, yes, so where are we going with all this? So I show you a number of different technologies that we're working with, and our goal as a company is to be able to offer a unified API, unified approach to deploy things to onboard computers. So as you know, the number of the variability of onboard computers, the family, is so large that it's impossible to cover them all. But we want to cover at least those that are quite used in the market, and in terms of CPU and in terms of hardware acceleration. No? So the idea is that, okay, you want to deploy your ONNX file or whatever you have trained. You deploy it with the Klepsydra API using our pipelining, event loop, etc. SDO, Klepsydra in the loop. And then internally, just by changing 1 or 2 lines of code, you decide if you're using the NVIDIA backend, the Xilinx backend, etc. So this is overall the concept we are working on and what we are currently covering. No? This is a little bit the roadmap, and this is the goal of the company in general. So at the moment, most of our work is being supported by the European Space Agency, as well as some defense institutions in Europe, and also some automotive companies. And I think this is more or less all what I have to present. Thank you very much.
Questions from in the room?
We have one online question. Are there plans to try running on Xilinx Versailles?
Yes, but we haven't started yet. We need to have the funding to buy one Versailles first, and then we will go for it. Yeah. Mm-hmm. No joking. Yes, it's true. We have it in our roadmap for next year. Mm-hmm.
So, you showed Linux versus RTEMS on the same platform. Any idea why there was so much difference? I mean, if it's compute bound, I would have thought they were pretty much the same.
So I don't understand the question.
You had one where you had 4 performance benchmarks, and they were like, one went from 7,000 milliseconds to like 5,000, that one. So, I mean, I'm happy to see RTEMS did better, but I'm kind of curious why, because I would have thought these were completely CPU bound.
But yes, but the thing is, there is a substantial overhead with the Linux in terms of multi-threading. That is not happening with RTEMS.
Okay.
But it's not massive. I mean, it's 700 milliseconds, one core, this coronal mass ejection model detection, 500 with RTEMS. I mean, it's a substantial gain, but it's not like.
So it's the process, so it's the overhead of swapping like the full MMU out?
Yeah.
Okay, that's pretty traditional when you're comparing benchmarks. Still a sizable jump.
Yeah, no, it was a great experience. The memory allocations as well are quite important because we use 0 memory allocations, but for some reason in Linux still there is some kind of overhead related to the memory usage that is not happening in RTEMS too. Mm-hmm.
Okay.
Great. Anything else from the house? Is it online?
No, nothing else. Thank you so much.
Thank you.